A server fan spins up. A CPU spikes for a fraction of a second. The perimeter firewall logs normal traffic, and the endpoint antivirus runs its daily scan to find a clean, secure system. Yet, deep inside the network, an attacker has already established full control. The security tools detect absolutely nothing. To figure out how the system was compromised, an incident response investigator isolates the very first file dropped onto the hard drive. But inspecting this file reveals that the code is heavily packed. Its true instructions are compressed and encrypted, wrapped in a protective outer layer designed to hide the payload. Analyzing a packed binary requires executing it in an isolated environment, so the code decrypts itself into memory. It is the digital equivalent of opening a Russian nesting doll, except this doll actively fights back against the investigator, attempting to crash the analysis tools the moment it realizes it is being watched. The investigator must carefully peel away this outer armor to reach what is known as the original entry point, the exact memory address where the unpacking routine finishes and the true malicious program actually begins execution. The most reliable way to strip this armor is by setting a hardware breakpoint on the stack. Common packers start off with a push-add instruction, saving all their active registers to memory. The analyst tags that specific memory address. When the unpacking loop finishes, the program pulls those registers back out to execute the true payload, which springs the trap and pauses the code right before the final tail jump to the original entry point. Once the true code is exposed in memory, the investigator dumps it to disk. Because the packer purposely scrambled the program's map of Windows functions, the analyst uses a debugger plugin called Scylla to locate the correct addresses and rebuild a clean import address table. Even in memory, the malware deploys aggressive physical countermeasures. The first is nanomites. The packer replaces standard conditional jump instructions with tiny int3 execution traps. If the program isn't running perfectly within its native packed environment, hitting one of these missing jumps instantly crashes the entire process. The second countermeasure is stolen bytes. The packer physically rips the very first instructions right out of the unpacked program. It executes those missing lines separately inside the unpacking stub, ensuring that any clean memory dump is permanently broken. The analyst meticulously patches the jumps and restores the stolen bytes. But when the binary is finally laid bare, the code is surprisingly simple. Defeating these intense physical defenses reveals that this dropped file was never the main payload at all. It is a decoy. With the decoy exposed, the investigation pivots away from unknown files and looks squarely at the operating system's trusted tools. This is a strategy known as living off the land. Instead of bringing custom hacking tools, the adversary relies on pre-installed utilities already native to Windows. The attacker silently deploys their true payload through PowerShell. To avoid leaving a readable script, they pass a massive block of base64 encoded text directly into the operating system using PowerShell's encoded command parameter. This lab document shows the exact PowerShell deobfuscation pipeline needed to intercept that payload. By enabling script block logging, Windows automatically records the fully decoded text to event ID 4104 the moment PowerShell translates it, capturing the clear text command. The decoded script reveals how the malware survives a reboot. Traditional malware creates auto-run registry keys, which are loud and easily spotted. This script establishes silent persistence by creating a WMI event subscription, instructing Windows to automatically run the malicious PowerShell command every time the system starts. By operating entirely within the boundaries of PowerShell and Windows management instrumentation, the malware avoids dropping a traditional executable file to the disk. Traditional file scanning antivirus tools see nothing but legitimate operating system activity. If there is no executable file on the hard drive and the PowerShell script has finished running in the background, where do the malicious instructions actually live? They live inside another program entirely. The core mechanism of this attack relies on code injection. The malware targets a pristine, trusted process already running on the computer, allocates a block of memory inside it, and forces that clean program to execute hostile foreign instructions. One highly reliable method discovered in the memory dump is early bird AP injection. The script creates a brand new, suspended Windows process. Before the operating system even has a chance to load its security monitoring hooks, the malware cues its malicious payload into the application's thread. Another observed technique is called section object injection. Here, the malware creates a shared section of memory between its own process and the target. This completely bypasses the standard Windows memory write functions that security tools aggressively monitor. The malicious code has successfully detached. It has no physical file, its scripts have terminated, and it is operating as an active phantom entirely within the physical RAM of the machine. To hunt a phantom, analysts capture a raw copy of the system's volatile memory and analyze it using a framework called volatility. It works like shining a forensic blacklight across a totally wiped digital crime scene. Standard tools like the Windows Task Manager fail to see the injected process because the malware uses direct kernel object manipulation. The malicious code physically unlinks itself from the active process list, lying directly to the operating system. Volatility's PS scan tool ignores the linked list entirely, sweeping raw physical memory for specific data pool tags that identify the process structure, immediately illuminating the unlinked node. Once the hidden process is exposed, the analyst runs the malfind plugin. This tool identifies memory regions that have execute permissions but are not backed by any file on the disk, directly locating the exact addresses containing the injected executable headers. By bypassing the compromised operating system and examining the raw physical memory structures, the analyst strips away the malware's final local hiding spot. With the memory footprint fully mapped, the investigation shifts outward to the network perimeter. The analyst uses Volatility's NetScan plugin to pull a list of all active and recently closed connections associated with that injected process. The results reveal a consistent, open outbound connection. The phantom process is actively attempting to phone home to a remote command and control server. The network traffic logs show the malware using a domain generation algorithm. Instead of connecting to a hard-coded IP address, it calculates and requests hundreds of randomized domain names. These DNS queries are easily flagged for their unusually high character entropy and low similarity to legitimate websites. The analyst extracts the outbound pattern, the destination port, and the unique HTTP user agent strings. They compile these exact data points into actionable snort rules, updating the perimeter defenses to block any future communication. The investigator isolated a heavily armored decoy on the hard drive and intercepted the fileless execution in PowerShell, extracted the injected payload from raw memory, and severed the active command and control connection. The enterprise is secured.